So I'm going to share the screen with you. I will be using the PowerPoint and possibly the visualizer as well to explain some of the aspects. Right. Good afternoon. So today, the last 2 weeks or so, we looked at more than 2 weeks actually. We looked at rectangular frames, and today we're going to start looking at pitch roof frames. I'm sure you have all seen pitch roof frames where you have a roof which is at some inclination. For example, in warehouses, in aircraft hangars, where you have got the roof pitched at some angle. Okay, and we have the actual theory itself is the same, except that for pitch roof frames there are some collapse mechanisms that we need to consider, and also the geometry is a little bit more complicated than that of a simple rectangular frame. Okay. So we are going to look at some pitch roof frames, carry out the analysis for a pitch roof frame, and I think the example I've chosen for today is that of a symmetrical frame. The geometry is symmetrical. And then we move on next week to something a little bit more complicated. And then we are going to construct and then interpret the interaction diagram, very much the same as we did with the rectangular frame. If you remember, when we had the interaction diagram to construct and interpret. Okay. So in terms of the geometry, we could have a symmetrical geometry. Right, the geometry could be asymmetrical like here, and we could have obviously multi-bay frames. I don't think we have time to cover this because we are already in week 6, and we still have a whole chapter we haven't covered yet, headline analysis. So we still have quite a bit to finish the syllabus. If I have time, I doubt it, I'll come back to this. Otherwise, we are going to focus on this to here. Okay. So we'll be looking, this week we are looking at symmetrical frames like this, where the geometry is symmetrical. And then we look at the more general case where you have the geometry and the loading also not symmetrical. And then we can see the difference between the two types of analysis. Okay, in terms of mechanisms, this is a typical frame, pitch roof frame here. Okay, the first obvious mechanism that you get in a pitch roof frame, very much like a rectangular frame, you get sway. Sway due to the horizontal load. So the horizontal load in this case applied at B, pushing to the right. So that will make the frame sway in this way. Yeah, and you have 4 hinges forming at the at A, B, D, and E. There is no hinge forming in the apex. This here we call this the apex. That's the angle. That's the pitch of the roof. So you have the as I said because this part will just simply undergo a simple horizontal movement. Okay. So the rafters here, the rafters BC and rafter CD will just will simply undergo a horizontal displacement, and therefore there is no hinge forming in the rafters themselves. Okay, so all we have hinges forming at the supports and the B and D in this case. Okay. The other mechanism that you get with the pitch roof frames is what we call a part sway. Okay. In other words, this is mainly due to the presence of the this is due to the vertical load pushing down. So when the vertical load is pushing down this way, what you might get a situation where the column here, column AB, remains straight, and the frame, this part of the frame will sway, which is what we call a part sway mechanism. Okay, which is a possibility when you with picture frames that you may get. Okay, and obviously then we have the combination of the two, the sway and the part sway mechanisms to consider. Okay, and we're going to do an example now just to show you how we can analyze each of the mechanisms in detail. If you have any questions, just stop me, okay? What I would like to do here, if I take you back, see that this rafter here, joint C, as you can see, will move down like this. So we have a vertical displacement of joint C, okay? And obviously there will be some horizontal displacement at C as well. Very small, but there is some horizontal displacement because of the sway. So when you have a sway here, obviously you have a vertical displacement and a horizontal displacement at C. And at D, you have horizontal displacement there, okay? So what I would like to do now, I would like to show you what's happening at rafter BC in detail, okay? So I'm going to take this here and basically magnify it and just explain a little bit about the geometry because we need it later on when we analyze the mechanisms, okay? So this is rafter BC. Initially, this is in solid white line. This is the original position. And this is after deformation. Once you've got, the deformation, and you can see that C has moved from C to this C dash. So this is the new position of point C. And then if you, so therefore at this end here, we have a vertical displacement, this one here, and we have a horizontal displacement. Yep. So if we call the angle of the rotation of BC to BC dash, if we call it theta, this angle is the slope angle. That's this angle here. If you draw a horizontal line there, that's your alpha. So alpha is the angle of the rafter of the pitch. Okay. So we have, and then by simple geometry, if I take this triangle here, I've rotated it around so it's easier to work out. So I have a horizontal displacement, this one here, and I have a vertical displacement, delta V, this one, okay? And the angle T alpha. You agree with me that if this is alpha, this is also alpha. Agree with that? Because it's 90 degrees. Because you've got alpha there, sorry. Because you've got alpha there, here, and this is a parallel line, so you got alpha at this here, this location. So therefore, this is also alpha because this is 90 degrees. Okay. So this distance CC dash is this distance times theta. You agree? Yeah. For very small displacement, CC dash will be BC or R if you want times theta, which I have here, okay? Then sine alpha will be the opposite, delta H, divided by the hypotenuse, r theta. And similarly, cos alpha will be the delta V, this side here, delta V, divided by the hypotenuse again, which is r theta, okay? Similarly, for sine alpha will be P over L over 2 over it will be P over R, hypotenuse. Yeah, so sine alpha is P over R, P, okay, over R, that's the hypotenuse. And then we have cos alpha, the adjacent, which is L over 2 divided by the hypotenuse, which is R. Is that clear? Yeah. Then I'm going to, when I equate 1 and 2, so when I equate 1 with 3 and equate 2 with 4, so that combining will give me delta H, the vertical displacement at C will be P, will be this distance here. That's the distance from the horizontal line there. Sorry, from the horizontal line to the it will be from the horizontal line to the apex, okay, times the angle theta. And similarly, when you combine 2 and 4, this equation and this one here, you get the vertical displacement L over 2 theta. The reason I'm doing this is because this is what we are after. We are after this equation. Okay, remember this. The vertical displacement here, because remember you got a V. There is V here. Yeah, we've got a vertical force or vertical load at C. Yeah. So the vertical displacement at C, this vertical here, this vertical displacement is equal to L over 2 times theta, times the angle of rotation. That is the only thing from all this. This is what we need to retain, to remember from this here. Okay, is that the vertical displacement is equal to L over 2 times theta. If we didn't do this, you would not have guessed what the relationship is between the vertical displacement and the angle of rotation of the member. Is that clear? Yeah. You don't need to remember all this. That's all you need to know, that the vertical displacement here at C, at the apex, is L over 2 times the angle theta. To illustrate it, we are going to take an example, okay? I think I'm going to use the visualizer so it's easier for me to explain. Is that okay? Yeah, because I think it's harder for you to okay, so I'm going to switch to the visualizer. That's it. So I'm going to, this is the example from the handout. So we are taking an example of, let me magnify it a little bit more. So we're taking the example of a symmetrical frame, okay? So we're looking at an example of a symmetrical frame, and the frame we have is this one. Okay, it's fixed at the base. And it is subjected to a vertical force or load V and a horizontal force H. They are critical loads, so they are already factorized. Okay, so the lambda, if you want, they are already multiplied by the lambdas. Okay, the bay in the horizontal direction, we have 8 meters and 8 meters. The height of the column here. The two columns, because it's symmetrical, we have 5 meters and we have 2 meters height from to the apex. Okay. Let's call this A, B, C, D. A, B, C, D, E. Okay. Now, let's use the rules to confirm what we said earlier, okay? How many possible hinges we have? 5, do you agree? 1, 2, 3, 4, 5, A, B, C, D, E. So we have 5 possible hinges. And the degree of redundancy, we have 3 unknowns at A, okay, because it's fixed. And then we have 3 at E, so we have a total of 6, minus 3 equations of equilibrium, which gives 3. Okay, so that's the degree of redundancy. Then the difference, m minus n in this case, is 2, and that's the that's 2. Okay, that's 2, and that's the number of independent mechanisms. Okay, that's the number of independent mechanisms. And n plus 1, in this case, 3 plus 1 equals 4. We 4 hinges needed or required for total collapse. So although we have a possible, we have the possibility of 5 hinges, we only need 4 for total collapse. Okay. So 2 independent mechanisms. We have mentioned them before. So the 2 independent mechanisms are sway of the frame and then part sway, which I'm going to explain now in detail. Okay. So please do stop me if there is anything not clear. Just say so. Okay? So number 1, sway mechanism. Okay. So that's the. So this is the frame initially. This is how the frame is. Okay. And when the frame sways, this is what we have. Okay, so that's the with the dotted lines. It is the new position of the frame after deformation. Okay, so we have A, B, C, D, E. So we have B dash, that's the new position of point B, C dash, and D dash. Because the frame is fixed at the bases at A and B, so we have a hinge forming at A and E. I forgot to give you here the MP. MP is actually given 50 kilonewton meters. Okay, and it's the same for all members. We have the same MP. We are going to take some examples in the future where MP is different, just to show you how you tackle this. Now, because MP is the same, so we have a hinge forming at there and a hinge forming at D. That's it. So we have now 4 hinges at A, B, C, at A, B, D, and E. If we call the angle at A theta, by symmetry, we also have theta at the other column, because we have symmetry, yeah? And the displacement, this horizontal displacement is the same. Remember this, okay? You have the same displacement at the top of both columns, okay? And delta will be 5, can you see that? 5 times theta. 5 times theta. You agree? Yeah. So we have the displacement is 5 times the angle theta. Very, very small displacement. Now, I always, I've told you before, I've said this before, I always show the direction of the plastic moments. Because if you need to draw the bending moment diagram, you know which direction are your moments, okay? So at A, we have got the moment at A is this way, that's MP. Then we have, this is also theta, so we have MP. And at D, we also have theta here, and we have MP. And finally, at A, we have MP in this direction. Do you agree with that? Yeah, it's always against the rotation. Yeah, the direction of the moment is always against the rotation. So if you take A, the rotation is clockwise, so you have the moment anti-clockwise, yeah? And then you do it for all of them. Yeah, so look at the member, in which direction the member is rotating, and your moment, because MP is an internal moment, it's a moment of resistance, so it goes against it's trying to restrain the member and prevent it from rotating. Is that clear? So it goes against the rotation because it's a moment of resistance. And these are the moments at each of the joints. Yep. So now all we do now is write the equilibrium of the works. External work is equal to the internal work for equilibrium. Okay. Now for the external work, remember that the sway mechanism is due to H. I mean, we do have V here, but there is no vertical displacement in this case. The sway will cause a simple horizontal movement. So therefore, the only work we have is the work of h. So therefore we have h times the displacement delta, which is 5 theta. That's the external work. There is nothing else. Equals, we have mp theta at A, we have mp theta at B, we have mp theta at D, and finally we have mp theta at E. So therefore we have 5h theta equals to 4mp theta, and the theta and theta always cancels. So we have h is 4mp over 5, which is 4 times 50 divided by 5, giving 40. So the sway mechanism gives us h equals to 40. Is the sway mechanism clear? Any questions? Yeah, thank you. So now we got to the path sway, where the vertical force pushes the frame down and make it sway to the right with the left column remaining straight. Is that okay? Thank you. So let's look at the path sway. So number 2, path sway mechanism. So this is the frame again. I'm going to draw it here. Can I ask you to draw the frame here a little bit down? Leave some space at the top. I'll tell you why in a minute. So this is the frame initially, and when it's so what we have the next, then the frame is going to this column here will remain straight, and the frame will just deform like this. That's how it's going to deform. Okay. So the vertical force V pushes down the frame, and it's going to sway to the right like this, with the left column remaining straight. So we have A, B, C, D, E, and the new positions we have C dash and D dash. I need your really full attention here, because I'm going to explain the geometry and how you get the angles. Once you have understood it once, you can use it for any other example, okay? Even if it's asymmetrical, you will understand it, okay? So please pay attention to what I'm going to say now, okay? So if I start with the with end B, and let's say that's how we start there with an angle theta. So I'm calling the angle at B theta, and obviously the angle at E will be different. Do you agree? Yeah. So the angle at B, let's call it beta, for example. At E, sorry. So we call the angle at E beta, and I need to find the relationship between theta and beta, because when I write the external work, I need to express it in terms of just one angle. Then I can simplify. I can cancel. Yeah. So anyway, so let's do that. So we say we have theta at B and we have beta at E, right? The next thing I'm to do, in order to find the relationship between theta and B, and beta, this is what you need to do. Please pay attention. You extend. Can you see this column here, DE? You take column DE and you extend it like this. Yes. Okay. Then you take rafter BC. This rafter here, not BC dash BC. Okay. You take BC and you extend it like this. The two will meet at this point here, which I'm going to call I. Okay? So extending column ED and extending rafter BC will give you a point of intersection I. Then I'm going to join that point to the new positions of the joints. So I join I to C dash, and I join I to D dash. Is that clear? Yeah? Obviously, my drawing is not to scale, so it may be a little bit confusing, thinking of the angles, because it's not to scale. Okay, bear this in mind. So I repeat, we extend ED, and then we extend BC. We have a point of intersection I, and then from I join to the new positions of the hinges. So I join from the joints. So from I to C dash, from I to D dash. Is that clear? Now, this is where you need your attention again. Can you see this distance here? It's the same. Do you agree? We have it's symmetrical. We have 8 and 8. Yes? Now, do you agree with me that BIC dash is an isosceles triangle? Do you agree that BIC dash is an isosceles triangle? Yes? Yeah. Because we have the same length here. So this triangle here, BC dash I, this one here, is isosceles. In other words, BC dash and C dash I are the same. So what does it mean? That means that the angle here is theta. You agree? Good. So the angle at I is theta there. Okay? Next, are you okay with theta at I, the angle is theta? Now, how do we find the angle here at I? What do you think?
Probably beta.
Okay, do you think it's beta? Why?
Because again, it should be not isosceles.
It's not, is it isosceles?
No, it's not.
It's not, okay. Yeah, it's not. We don't know, isn't it? We don't know. We don't know. Because it all depends on this height here. Yeah? This angle here, can you see this angle there? Concentrate on triangle ICD. Can you look at triangle ICD? Focus on triangle ICD. Triangle ICD has rotated to a new position IC dash D dash. Do you agree? By how much? By how much ICD has rotated? Look at the triangle. It was here. ICD. It has rotated to IC dash D dash. By how much? By theta. So what do we say about this angle? Exactly. So it's the rotation of the triangle. Okay? So triangle ICD has rotated to IC dash D dash, and therefore the angle there and there are the same. Although my drawing is a little bit, because it's not to scale, they don't look the same, but they're actually the same. If you draw it, if you do it on graph paper, and you draw your frame to scale, you choose a scale for your frame, and you do this, extend the lines, you would find that actually when you measure it with the protractor, you get exactly the same angle. Is that clear? So all you have to do is do it. If you want to do it geometrically on graph paper, you are free to do that. Okay? So therefore, the angle here is theta. Now, the next thing I need to do, really, I need to link. I haven't got the link yet between theta and beta. How do I get the link between theta and beta? Okay, let's try this. Let's try this. Okay. Let's draw a line here, a horizontal line. This is a horizontal line. Do you agree? Yes? Yep. This is a horizontal line. Do you agree? Parallel? Yes? Let's call this point here N. I want to do it slowly so you understand what I'm doing. I can give you the values, but you would not know where they are coming from, so I want to do it slowly. Do you agree that I, N, C, and I, D, B are similar triangles? Yes? I and C and IDB, similar triangles. Agreed? Okay. What does it mean, similar triangles? Similar triangles. What does it mean, similar triangles? It means IN over NC is equal to ID over BD. Do you agree? Yeah? So I have IN over NC is ID over DB. Now, IN we don't know. Do we know NC? What is it? From there to there. What is it? From there to there. 2. You agree? So that's 2. Equals. Do we know ID? We don't. But we know the ID is IN plus 2. Do you agree? Yeah? Divided by. Do we know BD? How many unknowns we have? Just 1. So I can solve. Yes.
In the video, you didn't do that one.
NC horizontal.
It's 8.
Sorry?
NC is
NC wouldn't
horizontal,
it be
so it's a
8?
horizontal 8.
It's parallel to this line. Yeah?
So isn't the length of it meant to be 8?
What, 2? Yeah.
Oh, sorry. Yes. I do apologize. Yeah, 8. Yeah, well spotted. So we have 8. Therefore, now we can cross multiply. Okay? So we have 16IN equals 8IN plus 16. Do you agree? Yeah. Throw this over the other side. So we have 8IN equals 16. So IN is 2. It just happened that in this case, IN and ND are the same. It's pure coincidence. If I give you a different geometry of the frame, obviously, you get different values. Is that okay? But the technique is the same. Okay? Do you agree? Yeah? So we've got IN. I needed that. Can you see this IDD dash, this displacement here? Okay. DD dash is equal to what? DD dash is equal to 5 beta, because this is 5. 5 beta. It's also equal to IN theta. Do you agree? Do you agree? DD dash is 5 times beta, and it's also ID times, ID, sorry, not IN. ID times theta. Agreed? Yeah. We know ID, don't we? ID is, what is ID? What is ID? 4. IN plus N, isn't it? I can put it here. ID is, sorry, it's 4. So we have 4 theta. So what is beta therefore? Beta is 4 over 5, not 0.8. Theta. Not 0.8 theta. So now we've got a relationship. So beta is not 0.8 beta. This method here that I've explained, the geometry that I've explained here, you can use it for any picture frame, whether it's symmetrical or asymmetrical, it doesn't matter. The technique is exactly the same that you use in this way, okay? And we are going to use it next week when we do an asymmetrical frame, yes?
Why is the slide you posted on Outlook different to here now?
What is different?
In what you posted on Outlook, the slides, you're getting different.
That one combined. I don't think that's the class.
Okay.
I don't think it's different. Is it different?
So when you look through the ones that you've posted on Aula, it goes straight to combined instead of having the parts way on.
Yeah.
Sorry?
So here you've explained parts way, but on your handout you explained combined. So it's still.
You mean I missed the pathway?
No, the parts way comes afterwards. So on the handout you did
As long as it's there. Okay,
Yeah,
I
it's
can
okay,
rectify. You mean the order?
Yeah,
Oh, the order, it doesn't matter. As long as the calculations are correct.
yeah.
That's okay. I mean, if, yeah, normally you do combined at the end. It could be when I was playing with it, I moved the slide. Okay, agreed with that? Do you agree? Yes? Okay. So we have got beta 0.8. Now we can, actually one thing I haven't done here, which I always ask you to do, is show the direction of the moment, okay? You can see that at BC, BC has rotated clockwise to BC dash, so therefore the moment here is MP. Yes? And again, BC rotating to BC dash, so we have, we have a hinge forming at B, obviously. We have a hinge at C, we have a hinge at D, and we have a hinge at and you can see that we've got 4 hinges, isn't it? Which is what we said, we need 4 for total collapse. So this is a case of total collapse, complete collapse. Yeah. So therefore we have MP here. And again, you can see the rotation of CD is going clockwise, so we have MP there. And then this is beta, and we have MP there, and finally we have MP.
Do we have an angle at C dash?
Yeah. Then we have theta and theta there.
Right, yeah, that makes sense.
Yeah. Yeah, and these are the directions of the correct direction for the moments, okay? So now we do the external work equal to the internal work. If you have got any questions, please do stop me, because it's vital we understand this question. Then we can do the ones in the future even more complex quite easily. Is that okay? Have you got any questions? Okay, so now we do external work equals to the internal work. Right? You can see that the external work is due to V because H is applied at B. See that? H is applied at B, so it doesn't come into play. Right? Do you understand this? If I give you the same problem, okay, with H on this side, that changes everything. Because then you will need to include the work of H. Is that clear? Yeah. So remember this, please. Okay. So we have got V times what is the vertical displacement from C to C dash? What is the vertical displacement at C? So it's V times the vertical displacement. What is the vertical displacement at C? Remember what we did there like some 20 minutes ago?
8 feet.
L over 2, which is 8 times theta. Exactly, because we proved it. Yeah, so it's 8 theta. Equals, that's everything, right? Because H is at B. Equals, we have at B, we have MP theta. So this is at joint B. Then at joint C, we have MP theta and MP theta. Okay, so we have MP theta plus MP theta. This is at joint C. At joint D, we have 2 members at joint D. We have member CB and member DB. So we have MP theta plus MP beta. This is at joint D. And finally, we have MP beta at joint E. And now all I need to do is substitute beta here by 0.8 and then simplify by theta everywhere. Okay, so we have 8 V theta equals 1, 2, 3, 4 MP theta plus we have 2 MP beta, and beta is 0.8 theta, right? So that gives 8v theta. 2 times 0.8 is 1.6. 1.6 plus 4, 5.6. And you can see that the theta and the theta will cancel. So therefore, we have V is equal to 5.6 MP divided by 8. And if you substitute, you get 5.6 times MP is 50 divided by 8, which, please do check it. Sorry? Is it correct, 35? Thank you. Is the pathway mechanism clear, please?
How did you get 8 again?
Which one here?
Yeah, the
V times the vertical display. We did prove it earlier.
Yeah.
V, it's 8 times the angle theta. Still its length times theta. That's the vertical displacement, okay? So it's 8 theta. It's okay? Yeah? Now we do the combination, combining the two together.
Oh no, what is this?
Do you want a short break? Do you want a short break? Carry on?
Carry on.
Okay, thank you. Combined.
So, could I just see the last part? Just for 1 second. Yes.
Right, so now we're going to combine these two mechanisms, okay? We're combining the sway with the path sway and see what happens. Now, look at this here, please. Can I have attention, please? In the sway mechanism, you can see that the column here, AB, rotates clockwise. You agree? Yeah, in the sway mechanism, the column AB rotates clockwise. In the path sway mechanism, beam BC rotates also clockwise. So when you combine the two, what's going to happen? If they are rotating in the same direction, remember what we did with the rectangular frame? The hinge will
90 degrees.
cancel because the column and the beam or the rafter are rotating in the same direction. So therefore, when you combine the two, the sway and the path sway, the hinge at B will cancel. Okay, so let's do it. So we have number 3, combined mechanism. I'm going to do it slowly because the geometry is a little bit more tricky. So bear with me, please. Now, when you combine the two, do you agree with me? Do you agree? Look at this, please. When you combine these two here, do you agree that the displacement at B and D will be different when you put them together? Yes. So the displacements at D, B and D will be different. So that's the first thing to remember, that when you put them together, you have a different displacement. So I'm going to reflect this into the drawing here. So I'm going to do it slowly. So bear with me because it's a little bit. So we have this, okay, at this end. Then we have something like I'm going to exaggerate to show that the displacements are different. So this is where this is the frame initially, okay, and this is after the formation of the mechanism, C dash and D dash. And you can see that the displacements, when you combine them, are different. Now, as explained earlier, the hinge at B is going to cancel. So we have a hinge forming at A, we have a hinge forming at C, we have a hinge forming at D, and we have a hinge forming at E. And you can see again we have 4 hinges, which is what we need for total collapse. Okay. So we start with the angle at B here, theta. So we call the angle at B theta, at A, we call it theta, okay? And let's call the angle here, because it's not beta, so let's call it, for example, gamma, let's say, okay? So let's call the angle gamma there. And my aim is to find, again, a link, a relationship between theta and gamma. Right? And I'm going to explain, again, the geometry, how you do it, okay? Right? So can I have your attention, please? In this case, this is how we do it. I'm going to explain it in I'm going to show you how to get gamma in 2 different ways, right? So you extend ED like this. So extend and column ED. Then next we join A to C and we extend. Is that clear? So you take, I repeat, you extend and column ED, and then you join A to C by line. You draw a line here from A to C, and you extend it, and the 2 lines will intersect at a point. So we can call it I as well, if you want. Okay? All right? Then we are going to join this point to the new, yes. We are going to join the new positions. Okay, so we join I to D dash. And we join I to C dash. And we join C dash to A. So this is a straight line. A to I is a straight line, okay? So we take a line from A to C, and then we extend it, okay? And then we take ED, extend it, they intersect at point I, and then we join I to D dash and C dash, and then from C dash to A. Which gives me now, can you see this angle here? This is here. Do you agree that this is an isosceles again?
Yeah.
Yes? Because we have the same length. So I C dash A isosceles. Yeah? You agree? Yeah? Now, If it's not clear, please shout, okay? Just let me know. Is that clear? Yeah, I repeat, you extend ED, and then you join A to C, extend it, gives you point I, and then from I you join to the new positions of the joints, so I to C dash, I to D dash, and then you join to A here to give you this triangle. Now, what is this angle here? Why? Same as we said before. If you look at triangle ABC, triangle ABC has rotated to AB dash C dash by an amount theta. So this angle must be theta as well. And because IC dash A is isosceles, this angle here is also theta. And then you have the rotation of triangle ICD to IC dash D dash by an amount theta as well. Okay, so this is, so I repeat again, AB, so we start with A, we call the angle here, the angle we call it theta. Then we have the rotation of triangle ABC to AB dash C dash by an amount theta. Then because IC dash A is an isosceles triangle, so therefore we have theta and theta at I. Then triangle ICD rotates to IC dash D dash by an amount theta. So the angle here must be theta as well. So the only thing I really need, so everywhere is theta except here, where we need to find the relationship between theta and gamma. Okay, so let me join these 2 points here together. So this is the horizontal horizontal displacement. How do we find the relationship between gamma and theta then? Any idea? I'll use the same trick, but slightly differently. What I'm going to do, please listen here to this carefully. I'm going to draw a horizontal line here. So I draw a horizontal line. Let's call this N. And then I draw this horizontal line. Can you see this? Can you see INC and IEA are similar triangles? Yeah? So we have INC and IEA, similar triangles. Okay? Therefore, we have IN over NC is equal to IE over EA. Now, IN, we don't know IN, so I leave it. NC is 8. Okay? Equals IE. Do we know IE? We don't. But we know the IE is IN plus NE. IN plus NE divided by EA. We know EA. 16. Yeah? So we have IN over 8 equals IN. Do we know NE? 2 plus 5? 7. Over 16. Now I can multiply across. So we have 16 IN equals 8 IN plus 7 times 8, 56. Yes? Then I bring this to the side, so 16 minus 8, 8 IN equals 56, so IN is 7. Agreed? And therefore ID will be 7 plus 2, 9. ID will be IN 7 plus 2, 9. Agreed? Yep. Nearly there. So what do we say? We say now that DD dash, this displacement here, is equal to ED gamma and is equal to ID theta. Agreed? We know ED. ED is 5, so 5 gamma equals ID. ID, we know ID. ID is 9 theta. So therefore, gamma is 9 over 5 theta. What is 9 over 5? Please. Is it 1.2?
1.8.
8, sorry, 8. 1.8 theta. 1.8 theta. So now we've got the angle at gamma is 1.8 theta. The good news is this: you don't need to do all this again in the future, because I'm going to show you a way of getting this same answer quickly. Okay? Because what was the angle? What was the angle? Can you see the sway mechanism? We had theta. Agreed? We had theta. From the sway, part sway mechanism, we had beta. Beta was 0.8. So when you add theta plus 0.8 theta, what do you get? Exactly. So we use what we call the principle of superposition. We use the principle of superposition. You worked out the angle for the independent mechanisms. When you put them up together, when you put the two mechanisms together, you can actually use the principle of superposition and use that to give you that angle without going through all this again. I wanted to show it to you how to get it from basic geometry, but you don't have to do it in the future. You just say principle of superposition. We got theta from one independent mechanism, 0.8 theta from the other, and when you add them up together, you get 1.8. Is that clear? Now to finish off this this combined mechanism, so we do the external work equals to the internal work. Are there any questions before we finish? Is that okay? Yeah. So what is the external mechanism? Look at here. We've got H. Yes, we have H and we have V, isn't it? So the external work, what is this displacement here? What's the displacement there? Remember, this is 5 theta. Good. So this is your horizontal displacement, yes? So we have H times 5 theta, that's the horizontal, plus the vertical load times what is the vertical displacement? 8 theta, exactly. 8 theta, because we have the same angle, equals, now we have, sorry, I should have shown the rotations there, the moments. So I have MP, we have MP, we have MP. This is gamma here. Then I have MP. I have MP, and finally MP. Imbalance. Is that okay? So these are the correct directions for your moments. Okay. So all we are going to do now is multiply MP by the respective theta at each of the joints. So we have at A we have MP theta. This is at joint A. Then at joint B there is no hinge at B. So at C we have MP theta and theta. You see there? We have MP theta and theta. MP theta plus MP theta. This is at joint C. At joint D, we have MP theta plus MP gamma. MP gamma, okay? So we have MP plus MP theta plus MP gamma. This is at joint D. And finally, at joint E, we have MP times gamma. MP times gamma. Joint E. And this is the equilibrium of external and internal work. And what we're going to do now, we're going to substitute gamma here by 1.8 and simplify. So I'm going to substitute gamma and then simplify. So we have 5h theta plus 8v theta equals 1, 2, 3, 4. We have 4 MP theta and we have 2 MP gamma, and gamma is 1.8 theta. So, which gives me 2 times 1.8 is 3.6, 3.6. So it's 7.6 MP. Yeah. So therefore, we can simplify the theta, and we have 5h plus 8v equals 7.6 times 50, isn't it? What is 7.6 times 50?
380.
Sorry?
380.
Thank you very much. 380. Is that the same as the handout? I hope. So we have 5h plus 8v, that's the horizontal times 5, the vertical force times 8 equals to 380. Is that okay? Any questions? Anything not clear at all? Yeah? Okay. So I'm going to summarize here what we've done. So I'm going to summarize. We had the sway mechanism. The sway mechanism gave us, I think, was it h equals 40? Yeah, h equals to 40. Then we have part sway. Part sway mechanism which gave V, I can't remember, 35. And finally, the combined mechanism gave 5h plus 8v equals to 380. So now I'm going to draw an interaction diagram where I have V in the vertical axis, and I put the H in the horizontal axis. This is a line here. So I need 2 points. So if I put H equals 0, H equals 0 will give me 380 divided by 8. Is it 47.5? Can you check it, please? Yes. And then if you put V equals 0, so you put V equals 0, so 380 divided by 5.
76.
Sorry?
76.
76, thank you. So we've got 2 points to draw the line. Is that clear? So now I'm going to choose an appropriate scale. You may do it on a graph paper, or you just do it nicely on a piece of paper. That should be fine, okay? So, so I'm going to draw here the interaction diagram. Okay, so interaction diagram. I'm going to do as I said, the H in the horizontal axis, and V, the vertical load, in the vertical axis in kilonewtons. Okay. Now, the maximum H will go up to 76, as you can see here, and V goes up to 47. Say 50 and 80. So I'm going to choose a scale here for H up to 80. So yeah, and then I put the vertical axis up to 50, so yeah, roughly. Okay, so for the sway mechanism, we have H equals to 40, and that gives me a vertical line. So H equals to 40, which is this here. This is sway. This is the sway. And then for the part sway, we have D35. So this is here 35. And we draw a horizontal line in this case. D equals 35. This is part sway. And then for the combined, we have 47.5, so 45, 6, 7.5, 47.5, and 76, which is 75, 76 about there. Okay, and then you join the two together. So this is H, 5H plus 8V equals 380 combined. And that's the interaction diagram for this frame, picture frame. Any questions? Okay. Anything inside this border, let's call this point, so let's call this P, Q, R, S, and the origin here is point O. So anything inside this border is safe, and anything outside is obviously unsafe. So now we have a number of possibilities. So let me get a piece of paper here to explore the possibilities. Okay, so PQ corresponds to part sway mechanism. So PQ corresponds to the part sway mechanism. QR and then QR combined. And then finally, RS corresponds to the sway mechanism. Okay, so that's what we have. Then we have obviously the points of interest, Q and R. Okay, Q, at point Q we have both path sway and combined together. Okay, path sway plus combined together. So this is what we call an over collapse. We have an over collapse. And similarly for R, we have sway and combined together. Again, this is another case of over collapse. We have another case of over collapse. Do you know why we call it over collapse? Why do we say over collapse? Sorry? Yeah, if you take, yeah, good. If you take, let's say, the sway and the combined, which is point R, if you can take these two together, if you put them together, if both happening at the same time, you will have a hinge here forming at B. So you will have 5 hinges at A, B, C, D, and E. And you need only 4 for total collapse. So when you have 5 hinges, it's an over collapse. In other words, you have more hinges than you actually need for total collapse. And that's why we call them over collapse, because what happened in this particular case is that you get 5 hinges forming instead of the 4 that you need for total collapse. Is that clear? Okay, that's the reason. If you want to find the coordinates for Q and R, it's easy. So for Q, we know that V is 35. So put V equals 35 into the equation of 5H plus V. 8V equals 380. And I think you get 5H plus 8 times 35 equals 380. I don't know, what do you get for H? You should get 20, but check it, please. Can anyone check it quickly? I think it's 20. Do you agree? Yeah? Okay, so Q, the coordinates of Q are H 20 and V 35. So this is for point Q. For R, what you do, you put H equals, for R you put H equals 40 into 5H plus V, 8V equals 380, which gives 5 times 40, okay, plus 8V equals 380, which gives V. I've got 222.5. Yes? Please do check the answers. Sorry. In order to get the coordinates of Q and R, all you need to do here is for Q, put V equals 35, gives you H, and for R, you put H equals 40, which gives you V. And I get these answers here. So therefore V is 40 and V is 22.5. And these are the coordinates. So this combination, this particular combination of H 20 kilonewtons and V 35 kilonewtons will give me an overcollapse where both path sway and combined mechanisms happen at the same time. And similarly for R. Any questions? Any questions? Okay. I'm going to show you how to draw the bending moment diagram for one collapse mechanism. The other will be the same. Okay. So we do what we did with the rectangular frame. I think I'm going to take the combined if you want me to, or the sway, doesn't matter. And then I show you how to explain how you get the bending moment diagram. Any combination here, any load combination on this border will give you a true collapse mechanism, will give you a true solution. Okay, as long as you are on the border itself. Okay. Any questions? So if let's look at the, let's say we want the bending moment diagram. For example, bending moment diagram for the combined mechanism. Let's say. So bending moment diagram for the combined mechanism. This is the frame. Okay, this is the frame. Look at the combined mechanism now. Can you put the combined mechanism in front of you and you tell me what direction, you give me the direction of the moments from the diagram. What is the direction of the moment at A? Look at your combined mechanism. Is it clockwise or anti-clockwise at A? Do you agree? So we have MP. Good. We don't know B, so I'll come back to B in a minute. At C, can you tell me left of C, is it clockwise or anti-clockwise? Anti-clockwise, so we have MP here. Obviously on the right, it will be clockwise for equilibrium. Tell me what is the bending moment direction at D in the rafter? Is it clockwise or anti-clockwise?
Anti-clockwise.
Clockwise or anti-clockwise?
Clockwise
Clockwise. So we have clockwise. Then we have anti-clockwise, as you can see here. Yeah. And finally, what do we have at E? Clock or anti-clockwise? At E. Do you agree it's anti-clockwise? Yeah. That's it. You see what I said earlier about showing the direction of the moments when you do the collapse mechanism. Because now when you draw the bending moment diagram, you know exactly the direction of your moments, so you can draw the diagram correctly. That's why. Okay. The only missing one, the only unknown in this here is the bending moment at B. That's the only one that we don't know. Okay, we know the moments everywhere. They are MP except at B. So what I need to draw the bending moment at B, and then I will be able to draw the bending moment for the whole frame. How do we go about getting the moment at B? Any ideas?
You make cuts.
Take a cut. Where? Where? You can cut anywhere. Where do you cut? Where do you take a cut? You can't do it in one cut, I can tell you. Remember what we did with the rectangular frame, isn't it? We did it in 2 or 3 stages. So same here. If you take a cut at B, the problem, if you take a cut at B, we don't know the moment at B, but we also don't know the horizontal reaction at A. So you have the horizontal reaction as well as the moment at B, if you take a moment at B, isn't it? So that's okay, but you have 2 unknowns. So we need to do something else. Sorry? Yeah, exactly. Because we know the moment at D and we know the moment at E, so the ideal one, we should start at ED. Because starting at ED, with the knowledge of the moments at E and D, I can straight away get the moment, the horizontal reactions at E. All right, so let's do that quickly. So I put here column ED. Yeah, so this is what I have. I have anti-clockwise at D, MP, and I have clockwise at E, MP. So this is D, E, and I know the height is it 5? Yeah, 5 meters. We also have the horizontal reaction HE. So I'm going to call the horizontal reaction at E H, right? And then taking moments about D. So moments about D. Clockwise, we have MP plus MP, that's clockwise. And then about D equals anti-clockwise HE times 5. So that gives me 5HE equals to 2 MP, which is 2 times 50 equals 100. So HE will be 100 over 5, which is 20. So we got HE. So we got the reaction at A. Sorry, we got the reaction at E is 20 kilonewtons. What I would like to do, in order to draw the bending moment diagram, you need values for V and H, isn't it? Because I didn't give you the values for the vertical and horizontal forces, right? But we are doing a combined mechanism. Okay, we're doing a combined mechanism. See, look at the interaction diagram. If I tell you to take this point here, where H is 30. Where H is 30, can we find the corresponding V or not? We can, from this, isn't it? So what I would like to do here, for this example, I would like to say, take H equals 30 kilonewtons. So V, can you work out V and tell me what is V, therefore? Can you work out V, please, for me, from that equation? Because I didn't do it. I think is it 130 divided by 8, isn't it? 5 times 30, 150 minus 230, 230 divided by 8.
28.8.
Sorry?
28.8.
28.8. Thank you. Do you agree, the others? When you put here H 30, do you agree you get V 28.8?
Yeah.
Thank you very much. So we know H and V. So what I have for this here, for this mechanism, I've got H is 30 and I've got V is 28.8. We know that, yeah? So going back to our calculations here, we got HE. HE is 20. Yeah, we got HE is 20. The horizontal load is 30. So what is the horizontal reaction at A? So what is the horizontal reaction at A? 10. Yeah, 20 plus 10, 30. Is that clear? So if we know H, we've got HE is 20, so the horizontal reaction at A. Now I can take a cut at B, because I know the reaction at A, so therefore we can take a cut at B, okay? Take a cut at B. So we're looking at column, AB. We're looking at column AB. So this is column AB. We have HE is 10. We have MP. And we have this height is 5 meters. Okay. I don't know the direction of MB, so I just choose any direction. Sorry? Oh, sorry. Thank you. So, so if I take clockwise, so if I take moments about B, clockwise I have 10 times 5 plus MB equals MP, which is 50. So MB, what is MB? Zero. So we got 0 for MB. It's just pure coincidence. If I've given you here different values for H and B, you'll get different value for MB. Yeah, but for this particular set, we've got the bending moment at B is 0. It doesn't matter as long as it's less than the as long as it's less than MP, the yield condition is satisfied, so it doesn't matter. Okay, but it's just pure coincidence that we've got MB here 40. You can try it if you want with different values of H and B, and then you can repeat this. You get different values. Okay. So now I can draw the bending moment diagram, and we are done. Okay. Okay, so we have refer to the diagram here. Okay, look at the diagram. We have tension on this side, tension at the bottom, tension at the bottom, tension at the top, tension on this side. Always draw the bending moment where you have tension. Okay, is that clear? So you've got tension on the left here, tension at the bottom there, and then you have tension at the top, and then you have tension on the left, on the right, and tension on the left at E. Okay. The reason we do that, so we plot the values of the bending moment on the side where there is tension to be consistent, basically. Is that okay? Now with this, I can now plot the bending moment diagram for the whole frame. I have MP and MP, so I can join. We have MP and MP. Then I have MP at the top, so that's 90 degrees perpendicular. I have MP here. Then I have MP there, and MP there, perpendicular there. Then I have MP on the left here, you can see. Remember that the bending moment at B is 0 in this particular, for this particular load combination. So I can join here, and I can join there, and I can join there. And that's the bending moment diagram for the whole frame. For V, for H equals 30 and V equals 20.8 combined mechanism. It's okay. Yeah, and you can do it for any mechanism as long as you know your your collapse mechanism, you know the direction of the moments, and then any missing moment, you work it out in the same way by taking 2 cuts usually, and that will give you the missing moment, and that's it. And then you draw your bending moment back. Okay. Any questions before we finish? Okay. Right, thank you very much. I shall see you next week. Thank you.
Thank you.
Thank you very much. I'm going to stop the recording.
Yeah, that's